Hello, good morning everyone. Today I am going to go through my one of the project or assessment where I did the FEA analysis on engine cooling. Okay, like this and this. Okay, and for the purpose, let's go through the paper from where I got all the reference. Okay, this is the geometrical data which is the same as mine. Okay, I follow this paper and I got these results. Okay, temperature at different conditions. Okay, heat flux, temperature, contour, this is all. Okay, and I did it on my own based on this paper. Okay, and I used two material. Okay, this is dimension, this is material, and for the paper, this is the paper. Okay, let's go through our presentation. Okay, then numerical investigation on optimizing engine cooling using different fin geometry and material on engine cylinder. Okay, as you can see, this is the air cooled fins that we use on the motorcycle. Okay, so we are going to use different fin geometry. Okay, this is the outermost content. First of all, I am going to engage on engineering background and review the research article methodology, ANSYS model simulation, and I will do extra scenario from the article and analytical modeling where we have to validate the model using the formulas and calculate making the Excel model. Okay, in the final we have to do critical evaluation and conclusion. Okay, first of all, for the farmers, why the engine cooling matters, why we have to cool the bike motorcycle engine or another engine, because as you know IC engine operate at high temperature around 80 to 85, but as a human we have only 37.6 degrees. Okay, around only we need to cool, needed to prevent the overheating, maintain engine performance. Okay, and reduce the thermal damage to the component, because at the high temperature the engine performance was not good and it can affect the engine component. So here we have fin cooling. Why fin cooling? Fin cooling is the minimum cooling system. In the engine cooling system, we don't need like the fan cooling from everywhere, because it will also reduce the engine efficiency. So we need to cool only little amount. Okay, so we need better fin system. For that, we need to analyze the shape of fin, what materials should we use, and thickness of fin. Okay, and cooling system, how should we apply that? And our research article that I saw a minute ago, they did the transient analysis for the different fin shape: rectangle, hexagonal, circular. There is three shape and three thickness of fin: 1.2, 2.2, 3.2 mm, and two material: NASA 398 and aluminum 319. Okay, overall 18 model were analyzed in that article. So I am going to follow everything from that article. Okay, so our main aim is to we have to find optimal fin which has uniform temperature distribution, identify best thickness, and we need a best material. So we have to carry out transient analysis and model analytical method to verify the temperature distribution. And for the methodology, what did he do? First of all, I designed the model, the engine with the fin in SolidWorks. Then I imported to the ANSYS Workbench in the transient thermal analysis, and I inferred our material geometry. Okay, we have two material, so we have two different properties. Okay, and I set up the geometry selection, material selection, that done. And in the mesh I did mesh analysis, and in the fluent I set up the boundary condition, and I did the analysis setting like the how much how much time should we do analysis. Okay, and I got the result. Let's go. And this is done in the article. Okay, for different thickness, from where I am going to do 7 to 12. Okay, and from the paper it's best is 2.2 mm, circular thickness of NASA 398, and I am going to verify that from my own analysis. This is the geometry. Okay, for the circular, hexagonal, rectangular fin, you can just copy it and try it yourself. Bye-bye. And this is my model. Okay, hexagonal. This is, and all of this I made in SolidWorks. And for the two material, this is the different density, CPCB, and thermal conductivity. From here, we can know that NASA 398 has the better thermal conductivity and specific heat. Okay, so I know it's gonna perform better. So we have to see it ourselves. For the boundary condition, I set up it inside temperature. Core temperature is 350 and convective heat is 10 watt 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 per meter square Kelvin, and ambient temperature 27 degrees Celsius. I simulated it for 100 seconds. Okay, and I left all of this for natural convection. And to tell you about this, I did all the analysis in ANSYS and I uploaded a video about the ANSYS simulation. You can go and watch this video if you want to learn about the ANSYS. And for the meshing, I did global sizing, okay, and local sizing. And for the transient analysis, for the solid analysis, the meshing matters, but it doesn't matter like it matters in the fluid analysis. So just to find analysis, so we have to calculate skewness, okay, aspect ratio, element quality, and these are my ANSYS validation. I did it for different sizing and I got around the same result like the heat flux, okay, like the temperature. And I did everything which need to be close to article paper. Okay, I just follow the article. I need to get the article result because I use the same geometry, same boundary condition. So I need to get article result. So I just follow everything. And for the temperature analysis, this is for the different temperature. Okay, as you see that for hexagonal, for circular, for rectangular, this is the temperature contour. Okay, and the below figure is temperature with time. As you can see, our circular fin reaches the steady state condition more faster than other because it has a uniform distribution in all directions. As you can see, in rectangular or in hexagonal, the structure is not good. At the tip, at the end, heat transfer is not good. That's why it takes more time. That's one of the conclusion from here. Okay, so we have to keep in mind that temperature, temperature, how much time one shape takes to reach the steady state condition. And this is also the heat flux. Here we can see that circular fin have the good time. It cools down so fast. Okay. So sharp edges of rectangular and hexagonal create the hindrance to heat transfer. That's why it's little bit slow. Okay. And these all conditions are almost similar to paper. And this is for another material. Okay. You can see this is for another material. And this is another material. So from here, from the article, we see that circular fins offer 25% more material saving compared to rectangle and 10% more compared to hexagonal. So circular fin has less weight, even perform better. Also that for the material NASA thin and they have the good properties, so it perform better. Obviously, and 2.2 mm thickness is the best, balancing both thermal stability and structural efficiency. If you use more thickness, it will be not that good. Okay, thermal, it will be not that good, and also weight is increasing, which we don't need that. So In conclusion, circular fins outperform both hexagonal and rectangular fins. So, which in the term of steady state response time material usage. Okay. So I did another material. So I increased the outer diameter because it will be more exposed. It will be more exposed to environment. So we will get the good cooling. Yeah, yeah. This is all. I get the good cooling. Okay, but the material is increasing, which will be our disadvantage. Okay, and to talk about the heat transfer, this is the governing equation of one dimension steady fin. Okay, just normal equation, and use the central difference formula to calculate the heat. Okay, for the different for this condition base temperature. Okay, I calculated the different temperature at different position. Okay, it we can see that from 1 to 2, if you have temperature 350 at 1, how much temperature will be at different position. As you can see, this is the different condition. So I calculated from the numerical method, also from the ANSYS. Okay, as you can see that in different position I have this temperature. Also using the Excel mode I got almost close value. Okay, I use all this method and I got the almost same value from the analytical Excel model and ANSYS model, which says that it's good. We are doing good. Then for the final, we got to know that transient thermal analysis is very good for analyzing cooling performance. Okay, and model shows that performance dependent on geometry and material. Okay, which is very important thing. Increasing the diameter increase the performance. Okay, by it expose more surface to the air, but also increment material. So we need to keep that in mind. So one day supported ANSYS result producing same result temperature trend. Okay, even there is only less slight difference in the value, but it's almost close. But here, comparing to the real condition, for convective heat transfer is assumed to be constant, which is not in real condition. Airflow around the fin is neglected. Okay, so real engine operating conditions are very simplified, and also ANSYS model doesn't include the thermomechanical stress issue. So this is only one day steady state condition because it vary with the time. Overall conclusion, we got to know that 2.2 mm circular fin is best model using the NASA 398. Okay, and in the model maximum temperature goes from 350 to 347. Okay, and heat flux is that, and the time taken to reach the state is 20 seconds. Okay, and that's all. Okay, I already did the ANSYS simulation and I uploaded that video in the YouTube. Go see that ANSYS simulation if you are interested in building your ANSYS skills. So thank you.